Okay, so I'm going to be presenting the early results from the HAFLANG project, which has been joint work with me and Rob for the last year and a little bit. And the whole project is about trying to accelerate the evaluation of functional languages by designing some truly custom hardware. So essentially making a special purpose processor for lazy functional languages. So since we're talking about lazy functional languages, let's start with some wisdom from one of the Simons. And this is him lamenting how much effort it requires to translate the high-level evaluation model, the graph reduction for a language like Haskell, down to something that you can directly run with the instruction sets of stock CPUs. Right, there's a big semantic gap there. And I'm sure this was delivered kind of tongue-in-cheek, but there's some truth hidden in there for sure. So to try and convince you that there is an issue there without going too into the weeds with different graph reduction techniques, let's look at one really simple example. If we have a function, even a simple one like this, just adding 3 integers together, the first thing we'll have to do when we have an application of this function is to construct a graph that represents the body of the function. So just looking at that instantiation, the construction of that graph, not the rest of the reduction, you can maybe try and imagine what the output should look like from a C compiler, something like that. But when we pump it through GHC without any optimizations, you get that. Just for constructing the graph, not doing the reductions. So at no point in this code are you actually doing the additions you wanted to do. This is just the fluff needed to get graph reduction to work on a stock instruction set. So what are we even doing here? There's some runtime stuff over here. So because the runtime is not generic enough to be supported in the hardware, every single time we instantiate one of these things, we have to check inline for stack space. If it's full, jump to the runtime system and scream. Do the same for heap space, possibly jump to the runtime system. For the actual construction from here onwards, we're kind of limited by the logical model we have of speaking to the memory. So there's only really one interface we can use there. So although we know we've got this graph we need to build with multiple applications, where each of the applications itself is built of multiple atoms, we can only do one little piece at a time here. So we're doing single move instructions to set up a single atom in one of these applications. And things get even worse on the other side when we're talking about entering closures, right? We have to go and retrieve some of the environment we stored. So there's a lot of work going on just to do the graph reduction part of this. And that feels like it should make us uneasy, I think. In fact, a lot of the extra work GHC will do is basically throwing a bag of tricks at this to make it look like it's not doing graph reduction anymore. So our goal is to try and do this, but a bit more directly, see if we can get this down to instantiating the graph in a single cycle. That's kind of the aim of the game here. So in broad strokes, what we're going to do is suggest, instead of this conventional model where you've got your application code, but then a big software runtime system sitting above your hardware, we're just suggesting we kind of lift up the responsibility of that hardware layer to include language-specific things like the graph reduction, garbage collection eventually, maybe also handling parallelism, slightly finer level. Also, we're by no means the first people to look at that. Right, Rob curated a really nice interactive page. It's on our project webpage here. Kind of listing some of the important historic efforts at exactly this. And I think there are kind of two really important eras here. You can see there was a lot of activity in the 80s and 90s. It was a really hot topic in that time, but I think in general, they were kind of limited by the accessibility of prototyping these digital circuits. Right, back then, to build a custom machine, it was buying off-the-shelf microprocessors and arranging them in a novel way on a PCB that you've had manufactured. Right, so there's always a little bit of playing catch up with the advances in the sort of RISC microcontrollers, right? So that kind of died away with improvements in the compilers for these languages for stock CPU architectures. But there's a little bit of a resurgence around 2010. There's a few projects that were now able to actually explore properly custom circuits through these FPGA devices. So these are really little platforms that let you rapidly prototype your own circuits. So we're not talking off-the-shelf CPUs anymore. These are properly custom. And you can think of them a little bit like a software-defined network, but at the nanometer scale, right? So you've got customizable routing and you can control what each node in that does to a certain extent. So that little resurgence was very interesting. And there's one project in particular, the Reduceron project from York University, that I think did a really nice job of exploring up to the contemporary limit what you could do with these devices. So they ended up with a nice single core architecture that we are kind of extending and building upon now. But the ceiling there was running out of on-chip memory, and there's nothing else you can do. So they got up to the point of having a single core. Beyond that, things get difficult. So we're coming along another 15 years later or so, and just seeing what the state of play is, what we can do now. So just in general, we think there are a couple of different opportunities we have when we design something from scratch. The first one is trying to exploit some of the parallelism that's present in the definition of a single function. So we saw in that assembly example, there was no reason why we couldn't instantiate that entire graph or something more complex at once, right? But through that compilation process to stock CPUs, you end up having this big sequential task you're doing. So we can better design our memories to let us do more work per cycle. And that pressure on the memory is much worse for pure languages, right? With immutability, you're going to be allocating parts of your data structure again and again and again. But also, it's even worse for lazy functional languages because you're also allocating funcs all the time. And they all live in the same memory. So the second point is the historic promise of all of this parallelism that's inherent to pure functional programs. Some of that will exist at a level that is just too fine a grain to really make good use of with stock hardware. So if we can accommodate that a little bit better, we can expose more of the parallelism in an actually usable way. And finally, there's all this runtime system that's sitting about that usually we have to pause the useful reductions to manage, and then we context switch back to doing the reduction. We're hoping we can do a lot more of that in parallel to the useful work. And most of this is just going to be about the first topic. I'll talk a little bit about the other two and what we're planning to do, but that's very much a work in progress. Okay, so what would a special purpose processor actually look like for this? I think for this audience, the best side of that to start from is the instruction set. So if we're trying to very directly evaluate a functional program, what does the instruction set look like? Well, let's just make it a non-strict functional programming language itself, and then job done. So if we're looking through what our assembly with air quotes is, it should look really familiar. It's just a program which is a list of top-level function definitions. Everything is lambda lifted, so we only have top-level functions. We don't have lambdas floating about. And we massage them into some administrative normal form. So every function is a single let expression. It might bind various applications, and the body of the let expression is also an application. The applications themselves, we're working directly with potentially quite wide structures. We're not currying everything. We're trying to exploit wide hardware. And we also have to tag what sort of application it is. So we've got sort of plain bog standard applications. If we know we're doing some primitive operation, there are certain optimizations we have for that. But the only slightly weird one is the case application. So this is really the only slightly tenuous thing here, where for a case expression, we lift all the alternatives up to their own top-level functions. And then once we reduce the subject of the case expression, we use that constructor tag just to index into a list of all of the alternative functions. Right, so the subject gets wrapped in one of these case expressions. Beyond that, it's just the usual suspects, right? So we've got things to support constructors for user-defined data types, primitive integers, operations on those integers. But then we have 4 different sorts of pointer, and we maintain that distinction between the 4 pointers. Back in the assembly example, it would all be just a pointer, right? There's one logical memory we're going to use, so there's no reason to make this distinction, but we do for a good reason. The last thing to be cognizant of is our circuit is going to be a fixed size structure, right? So we have to be kind of wary of any of these dynamically sized listy things in our syntax here. We have to put upper bounds on the size of those things, essentially. So to give you an idea of what those bounds actually look like and what they dictate, I've got one example function. It really doesn't matter what it's doing, except that it's in this administrative normal form. It's a single let expression, right, with 2 applications that are being bound. The bounds we have to put on this to make it compatible with a processor configuration here. Well, the first one, the body of that let expression, we're going to construct it and push it straight onto some stack memory. So our stack has to be parallel enough. We have to be able to access enough elements simultaneously to push all of those atoms onto it. So we've got one dimension there that controls something about our stack implementation. There's a very similar but separate dimension controlling any of these let-bound applications, because we're going to build those and chuck them directly onto the heap. So that controls how wide a single word in your heap memory has to be. And the third really important one is the number of let-bound applications we can instantiate at once. It's really common to have dual memories, so you can do 2 independent operations in one cycle. There are tricks we have to increase that past 2, but we still have to respect that bound. So our processor to support that sort of assembly language is really, really, really simple, kind of embarrassingly so. So we've got in the middle just this control logic that is not pipelined. It's a simple state machine, really. That's all it is. And the way we try and widen that bottleneck to the memory that we saw with the assembly example is just encircle this control logic with lots of independent memories. right? And beyond that, they're not just independent, so we can access all of them simultaneously in one cycle. Most of them are quite wide. So the template memory, the code memory here, that's going to be storing an entire let expression in one entry. So somewhere in the order of 300 bits or so. For the heap, we're storing entire wide applications, and for our stack, we can access the top n simultaneously. And one more trick to widen that bottleneck a little bit further is having parallel access to each memory. So for the heap memory, in this example, we have two independent ports, so we can do two wide operations at the same time. All of that is really quite basic stuff, but it requires you to have a properly custom processor design. So the downside of having this really simple design that's not pipelined is, well, it's all stack-based. Everything we do is going to be directed by what was left at the top of the stack by the previous cycle. So I'm saying it's not pipelined. We can get good performance without it, but really it's because it's hard to pipeline, right? There's this data dependency between every single adjacent cycle. But there's only a few different operations we have to support here. So if we look at what could be on the top of the stack, first one, just primitive integer. As long as that's not the final result of our program, we know it's going to be part of some primitive operation. So all we do is we pipe that through to the ALUs, and we can write the result back to the top of the stack. Could also be a pointer to an application from the heap. All we have to do is read that from the heap and push its contents to the top of the stack. There are some accounting operations that go on the side here. We do some tracking to avoid doing updates when we can. So if there's ever a reference to an application that we know is definitely not shared, there's no reason to then overwrite that application with its normal form, right? Because it's not going to be needed again. So there's some accounting up to the side, but really it's just reading from the heap, pushing onto the stack. So again, simple sort of canonical implementation of this. If whatever at the top of the stack is in normal form and we do need to update it, then we will have to write it back to the heap. Simple enough. But the only kind of interesting operation here, the fun one, is doing the function application, in which we touch nearly every single memory in the whole system. So instead of using very complex pipelining to keep all of our different units busy, with function application, we've just designed it so it will need to touch every single part of the system anyway. And constructors for us, because the way we've set up the case alternatives as functions, that's kind of just a special case of function application. Okay, so that is the gist of our actual architecture for a single core. A lot of this, though, is a shared foundation with that reducer-on project I mentioned, just presented in a very different way. So we've gone a little bit beyond that. We've completely re-implemented it in a different circuit description language. As part of that, we have a parameterized design by those three dimensions I was talking about. So we don't just have one processor, we've got a whole family of slightly differently configured processors of different shapes and sizes. So we can explore the non-functional properties of those circuits a little bit better than we could in the past. There's also a few semantic changes we've made. Previously, there were a few different potential conflicts between subsequent cycles, and that was just very conservatively dealt with a compiler pass. So you'd often be underutilizing the dimensions of your templates just to avoid these hazards you can have. We've moved all of that into the runtime. So very small additions to the circuits to detect that dynamically at runtime. So most of the time we've got better throughput. Occasionally we will have to stall. We handle case expressions a bit differently. We can encode very trivial base cases that appear all the time inline. And that's really important because the templates are allocated as quite big chunks. So if we have these tiny base cases all over our code base, that's going to end up using quite a lot of the code memory. And the memory was really the limiting factor for reduce run. So any saving we have there is quite valuable. And probably the most tricky of these is that we realized it was very easy for us to make in hardware these parallel accessible stacks. But it's not always very easy for the user program to make use of such wide applications. Often there'll be much more deeply nested but shallow applications. And we wanted a way of trying to lift those up, kind of flattening them into something more suitable for our hardware. So one way we've got of doing that is we put all of our primitive operations in postfix. And with help of one extra stack, it means we can use reverse Polish notation. So we can flatten those, well, some of the deeply nested narrow applications into flatter, shallower, but wide applications that our hardware is better suited for. So that kind of translates to a few improvements. Just targeting a modern high-end FPGA with some thoughtfulness behind how we map our design onto the new resources. It means we've increased the maximum clock frequency by, well, it's doubled. But the really exciting thing and the low-hanging fruit for us now is what used to only just fit on one of the contemporary FPGAs is now under 2% of quite a high-end FPGA. So the obvious thing for us to do is to explore throwing down lots of these cores and trying to coordinate them in some interesting way. Our changes to the semantics, we get a little reduction in the number of cycles just because we've increased the throughput a little bit with our dynamic detection of these hazards. We get a pretty hefty reduction in code size. And again, even for this 2%, that's limited by our memory usage. So reducing the code size is quite valuable. And also reducing the number of heap allocations we do, which should lessen the pressure on any garbage collection that we'll be looking at quite shortly. Okay, so we do have actual physical results from our circuit. There's a couple of different ways you might want to measure that, but first of all, because we have a parameterized design, we're playing with those 3 dimensions. It lets us explore the non-functional properties of different circuits, and that wasn't possible before. So we're varying 2 of those dimensions here. One controls how parallel the stack implementation has to be. One of them controls how wide your heap memory is. But when we're looking at these circuits, the 2 things that are really important are, well, space and time, right? So how big is your circuit is this max resource usage. This is just how much of a single FPGA our processor occupies. So directly, how many cores we could fit onto one chip. We've got this suspiciously uniform pattern here. That's just because with our arbitrarily chosen heap size, our maximum resource usage is just the heap memory. But if we were to choose a different size, you wouldn't see that pattern. So let's ignore that for now. You get a much more natural kind of transition from small circuits to large circuits here. So we're always sitting comfortably below 2% of a chip, which is a very different playing field than what we saw in 2010. The other non-functional property is the maximum clock frequency you can run these things at before they fall over. And as you'd expect, the smaller designs can be clocked a little bit faster. Again, in a fairly uniform pattern, it degrades to, well, from almost 200 megahertz to 150 or so. But that's not quite the full story, because the smaller designs will take more cycles for the same benchmark, because the templates have to be smaller. And if you exceed those bounds, we have to split things into multiple templates. So it's not just about how fast we can clock these cores, it's about the actual wall clock time needed to evaluate some benchmark program. So we've done that analysis for our test suite, and we end up with this slightly anomalous point out here being our best one. I think this is just the vendor tooling kind of being tricked into swapping some flag based on the size of some structure. There's no fundamental reason why that should be faster than the ones around it, but that is the best configuration for us anyway. So if we take that, we can then start comparing it against implementations with GHC running on stock CPUs and see where we end up. And that's very much a stepping stone, because we always intended this to be a multi-core design. Just now we've got to the stage of having a single core. So we're taking a break just to try and evaluate this, but it's not going to be the final conclusion of the project, hopefully. So we can compare the number of cycles we need to evaluate a set of benchmark programs. And we're doing that against two Intel processors, both mobile processors. So we've got the i7 that is in this Dell XPS 13, and there's an older i3 that's in one of Rob's computers. And we can see that for every single one, our Heron core in pink needs way fewer cycles, which is what we would hope, right? We've tried to design this to do more work per cycle, but because we're not pipelining it, we're going to be running at a slower clock frequency. So in average then, we've got, compared to the older i3, nearly 10 times fewer cycles for Heron, and the i7 needs about 7 times more cycles. Interesting to note the difference between the i3 and the i7 there, although they're using the same instruction set. That will just be effects of their pipelining strategies and branch prediction and all of the complex stuff you have to throw at the graph reduction problem if you're using a really deeply pipelined architecture. So we've just kind of sidestepped that by not bothering. However, our core runs about 10 times slower than all of these, right? So that is not a comparison of wall clock time, that's a comparison of cycles. So let's be a little bit more fair. Let's look at the actual runtime and also the power usage of each device. So I'm plotting 2 points here that are both our Heron core. They're just targeting different FPGAs. So this Alveo one, that is the board we would like to use for our big multi-core system for the end of the project. So that's the one we can fit 50 cores on. Meaning almost all of it is unused, but we're still committing to that power budget of keeping the whole device alive, right? So the power consumption of this is going to be very pessimistic. So we're also including this other data point, which is a much cheaper, much smaller FPGA, where you can fit about 3 cores, but it is a lower grade device, so it runs a little bit slower. So we've got optimistic performance results, like wall clock time, and optimistic-ish power consumption as our 2 reference points. So let's compare that against some embedded CPUs, 2 ARM configurations. And again, we're measuring the power consumption of the entire chip, so that's including any idle cores, but they have quite aggressive frequency scaling. So I think this is as fair a comparison as we can make with a single-threaded benchmark. And for our cheaper implementation here, with the same power budget, we're either outperforming this 2.5 times or about 5 times, which was a nice surprise. This was always a stepping stone, right? This was not the end of the project. So in the embedded space, we're looking pretty healthy. You could argue about embedded applications for these languages. Maybe this is why there aren't any, but if you know of any, please let me know. But on one extreme with the embedded stuff, we're already looking quite comfortable. Things get a little bit more nuanced when we consider any of the higher end Intel, even mobile desktop or server processors. Right, so if you only care about absolute performance in terms of runtime, this i7, so this laptop I'm presenting with, that's still going to run on average about 2.5 times faster than our single core. And I think Rob had a good idea of what HAFLANG should mean for the project name, but I'm going to co-opt to that and claim it's that I've taken a language and I've made it run half as fast as it used to. So we're in the same order of magnitude, and that gap has closed quite significantly compared to the Reducer-on project, which is also nice to see. But it's quite rare that you only care about the absolute performance in terms of runtime, especially if you're doing something on scale. You care more about performance per watt, right? Because you're going to have to pay money to keep these things running. So performance per watt is really the metric we're going after here. So I've plotted on just a constant performance per watt, so it's 1/x scaled by something. And we can see even though most of this device is empty, doing nothing, we're getting more competitive with the Intel mobile processors. But the outlier here is this cheap implementation. It's really the only major outlier from that line. So that's suggesting that for a single core, we already have quite a good performance per watt, even on one of these like low-end FPGA devices. So that is the takeaway. That's the encouraging part. We have a good performance per watt and room to scale it up. If on top of that, we can exploit parallelism on a slightly finer grain, that's even better. But we've got a really encouraging foundation for that future work. So there are two topics that we're currently working on. The first one is we don't yet have hardware garbage collection, but that's what I'm actively working on now. There are two quite neat observations that are going to inform what we do there. The first one I think is really cool. In our core, we have update avoidance. We track for each application if it's possibly shared or if it's definitely not shared. If it's definitely not shared, we never have to overwrite that with its normal form. We do that actually at runtime in the core in a way that would be prohibitively expensive for software, but we just have a small little circuit sitting to the side doing that detection and updating those flags. So that's an important feature we need for one reason, but it's also exactly the same as doing 1-bit reference counting, right? We know if an application only has one reference to it. So when we unwind that from the heap, put it on the stack, if it's not shared, we free it. And for us, that catches over half of all of the garbage for a feature that we already had, which I think is not bad. Part of that will be because for particularly wide applications, we will split them into multiple applications chained together in a way that is not shared. So that's probably not the same for a traditional software implementation, but for us, one feature we already have more than halving the amount of work we have to do is pretty neat. The other thing we're pretty tempted to follow up with is we can pretty easily preclude cycles in our heap data. The only way we can introduce cycles is through letrecs, right? If we just in the compiler instead lift those up to a set of mutually recursive supercombinators, we can't introduce cycles on the heap. So that means we could have really pretty simple support in hardware for reference counting and call it a day. And that's particularly appealing because the reference counts, the operations to that are kind of time insensitive. You have to be careful about the order you do things in, but you don't really have a strict timing deadline. So we could do that off to the side. We've got this carefully tuned core for the reduction, where any damage to the clock frequency on that would really hurt us. But with the reference counting, we can do it off to the side in a pipelined, entirely separate bit of circuitry. The other reason that is kind of neat, I think, is it gets around a lot of the issues we see in software garbage collection. So for a parallel system, it's really common if you're doing some sort of mark and sweep or copy and collector, it's really common that you have to give in at the global garbage collection events and just stop every single node, right? You have to have a single snapshot of the entire system in a stable state to identify the roots of all of the applications you're going to follow through. And that's just a difficult issue to solve unless you're doing reference counting and all the information is stored at the application rather than at the references to it. So for our parallel system, this could maybe scale a little bit better. That's easier to do with reference counting. Also, because with reference counting, we can do incremental garbage collection, we can make better guarantees about the worst case time needed to free something, less so about the allocation, but you get better guarantees about the behavior there, which might encourage some embedded use, which would be good for our processor, but that's an application area we still have to think about a little bit. And perhaps the biggest one is with this incremental garbage collection, your performance doesn't degrade if the heap residency is quite large. For mark and sweep, as soon as your working set is kind of getting towards the heap size, you're triggering more and more garbage collection events, and each of them take longer because your sweep stage is going to be, sorry, your marking stage is going to be proportional to the live data. So if we do something with reference counting, we can actually get away with much smaller heap memory sizes, and that is the upper bound in our circuit area. So if we can just reduce that a little bit without affecting performance, that would be a nice win too. Okay, so the least well thought out part of this is still on how we're going to orchestrate a multi-core system and how we're going to turn that into a parallel graph reducer. So the only thing I'm going to say on that just now is there are quite interesting analogies between the more successful previous attempts at this and modern FPGA architecture and tooling. Like really quite compelling, I think. Probably the most successful attempt at this previously was the GRIP project with Simon PJ and Chris Clack, and then later Kevin Hammond. they had an actual absolute speed up through their parallel implementation. So they have all of these different independent graph reducing cores. They also spend a lot of time in the literature about GRIP talking about this communications medium, which required a lot of effort. So it's this packet switched bus. It's got packet queues reordering. A lot of engineering went into that because that is easily the bottleneck in a system like this. And then they have on the bottom here this shared memory, but distributed shared memory. So it's a single address space shared between all of these units, but it's split into banks, and there's one controller with some intelligence that understands graph structures in front of each one. So it is a shared address space, but it's split up into these banks. So what do we have nowadays then? Well, we've got the single core implementation of a graph reduction core, easy. This communications medium that they spent a lot of time engineering, well, now that is the default vendor supplied bus. So nowadays you drag and drop that in a GUI and you have yourself a packet switched network that can do reordering, and it can do these handshaking protocols in a suspiciously similar way. So there's a lot of really good foresight there on their part. And for the FPGA board we have, on the same package, we've got this high bandwidth memory module, which is exactly that distributed shared memory architecture, where you've got, for us, it's actually 8 gigs, but all of these separate banks of sort of DDR style memory, each controlled by their own controller, and there's some network interfacing in front of that. But it's exactly the same architecture. So this feels like an obvious way to get something up and running that we can then play about with. But yeah, the best historical reference is now exactly what we have access to. So our plan, I think, is to go ahead with that. And there's lots of work to do on the language side of exactly how you want to spawn parallelism, and if we can do it entirely implicitly so the programmer doesn't have to give any annotations. That's all up in the air, but that's the main focus for the rest of our project. And just to finish up, me and Rob have a workshop coming up that's co-located with HPCA. So it's in Edinburgh. This is March next year. We have a call for papers or lightning talks. Deadline 20th of November. But even if you're just interested in this sort of stuff, it'd be nice if you'd come along, and we should have some big names there, hopefully. And also potential funding for PhD students, if you know of any people that might be interested. But apart from that, that is our early work here. We've got quite encouraging results with a single core that is now very small compared to these devices, and a pretty obvious path forward to exploring a parallel graph reducer machine. So that's me. Any questions? I'll happily field.
So that's really cool. What if I wanted a eager by default machine? How many of the insights sort of transfers, what doesn't transfer?
Yeah, good question. I think that necessitates custom hardware very slightly less, because part of the pressure we're relieving is to do with the allocation of thunks all over the place. Yeah, for how beneficial a truly custom approach to that would be, I'm not sure. That's an interesting thing to look at. It's just that the order of evaluation there is something you know more about statically, right? So the compiler techniques you can throw at that, I think it's a little bit more extensive. But good question.
Yeah.
So I know there's GRIN, which is basically optimal graph reduction. How does this relate with is this something you could basically build into the hardware so it will always do the best order of reduction?
So GRIN is, correct me if I'm wrong, but that's towards compiled graph reduction, right?
I'm not entirely sure, so that's why I'm asking.
Okay. There are definitely other projects we've come across that lean heavily into the optimal beta reduction stuff, like HVM is probably the biggest one.
I mean, GRIN is compiled graph reduction, but the key contribution of GRIN is that it's a whole program optimizer. You know, GHC is limited to the boundaries of a Haskell module, whereas with GRIN, it can optimize, it can perform GHC's optimizations, but across the boundaries of modules. And so it's a whole program optimizer, unlike GHC, which is an incremental optimizer. But as Greg says, it's still in the world of program graph reduction.
Yeah, for us, part of the appeal of this custom hardware is as directly as possible evaluating the user's listing. So to do that, we have some of those optimizations that you can do better with whole program optimization, like sharing analysis, that sort of stuff. We just do that at runtime at very little cost. So it's kind of fundamentally quite a different approach. We did start the project though by trying to evaluate whether we should go with this very simple template instantiation approach where it's not pipelined, and in fact it's quite hard to pipeline, or if we go down the route of having compiled programmed graph reduction and a really deeply pipelined architecture. And there was one project that started down that deeply pipelined route called Pilgrim, kind of contemporary with the Reducer-On project. So we picked up their semantics and played about the simulations and realized it was going to be a lot of engineering effort to get to the same performance as just the very simple, small alternative. So we've gone for the simple option in part so we can scale up a bit better. But that does come with the pretty hard ceiling on the single-threaded performance, because we're not going to get it much faster than it is now, right? Without having pipelining. Yeah.
Okay.
So, like, how does a non-functional language, let's say it's compiled down to this instruction set?
Yeah, so that's something that we've been asked a couple of times, and I still don't have a great answer. I think it's kind of related to Philip's question about eager by default. Right? Are there many lazy but non-functional languages? I honestly don't know. I'd be surprised. So you kind of have the same issue there as
60 years back, algo.
Okay, well,
right, algo.
Big audience for hardware.
Yeah,
so we kind of have the same issue there, where we're not totally certain about how strict or eager evaluation translates to this. But that's something we should definitely have a better look at. And, yeah. Okay.
A couple pointers that may be interesting.
Uh-huh.
So you do already have some analysis that tells you when you can sort of deallocate memory that you no longer need. Some of recent work by Dan Lyon, I'm not sure you're aware of because it's much higher level, is on sort of reusing memory in his implementation of stuff in the cases where there's only one sort of consumer, to not need to deallocate and reallocate at all, but just to reuse the memory.
Okay.
And that's in part to do with how he compiles sort of zipper-like stuff, and something to do with evaluation context as well.
Okay.
And it would be interesting to see if some of that, because of the runtime information you already have, could be sort of built into the compiler for cheap, possibly.
Yep.
And the other is for parallels, and some of the stuff I worked on way back when was to do with this sort of estimation of how costly stuff is, and spawning things on sort of implicitly, but only when you've done enough work to sort of amortize away the cost of a spawn.
Yeah, that would be ideal. I think we should have a chat about that. That's definitely the next unknown that's on the horizon, and the biggest blind spot of mine, although I know a lot of people in the department
I
can,
mean, I
can
would
help.
need to swap it in. So.
Sure. But yeah, that would be great. There's maybe even the opportunity of having these runtime dynamic analyses for things like the cost of spawning. That's something that's quite cheap for us to track in hardware, but would be ridiculous to do in software at runtime. So that'd be really cool.
I think we should wrap up. Thanks, Heriot, for the great talk.
Oh, thank you.
And we can continue our discussion for lunch.
Yes, perfect.
Thanks, everyone. To the room.
Right.